All right, in this video, I'm talking about gradient and directional derivative. I'm actually re-recording this video because I made another error. When I was making a sketch, I mislabeled one of the axes. But, you know, last time I told you the definition of the gradient, and it was basically a vector made up of all the partial derivatives. Probably should have this ready before I started recording, but I'm going to write down that if in the case where z is a function of x and y, what we call the gradient of f, we could also say the gradient of z, is going to be equal to the vector df dx and df dy. Now I'm going to tell you some more things about the gradient, like some geometric properties of it with compared to contour maps and level sets and everything. But I'm going to need to tell you a little bit about the multivariable chain rule first. And so in this video, I'm just going to be telling you how to compute the gradient, the directional derivative, and it will be very friendly to us. Okay, so I think first I'm going to just start off with a quick example. I'm going to say if f of x and y is x squared sine of 2y, find the gradient of f. And so what we'll need is we'll need the partials, and then we'll put them together in a vector. So the partial derivative of f with respect to x is going to be, well, I'll take the derivative of x, and anything with y, I'm going to consider it as a constant. Okay, and so that'll be 2x sine of 2y. And then fy will be, okay, I'll just consider anything with x to be a constant and take the derivative with respect to y. Okay, so I'll have x squared cosine of 2y times 2 for the chain rule. Okay, meaning that the gradient of f is 2x sine 2y and 2x squared cosine 2y. Okay, so this is friendly enough provided we know how to take a partial derivative. Okay. What I want to talk to you about really more today, though, is the directional derivative. Okay, now last time we talked about kind of this paraboloid that I think started at 5 and went up. I'm going to kind of draw you, I'm not going to write the equation of this thing, but I'm going to draw you kind of a paraboloid that's maybe starts at, so you could consider it starting at 5 and then going down. So that's a paraboloid. It's like a solid. And then now I'm going to draw in the coordinate axes. So this will be my x-axis. This will be my y-axis. And then my z-axis will come down like that. Okay, this is my paraboloid. So one thing that I think I mentioned, or at least I hope I mentioned, is in the partial derivatives video, was that if we take the partial derivative of, this function with respect to, say, y, what we're doing is we're pretty much, cutting into this thing at a particular point parallel to the y-axis, which will induce a curve, and then we're finding the slope of that curve. Okay? We're finding the rate of change when we bump up, say, y just a little bit. So what I'm going to do is I'm going to at least attempt to draw you this. So we're going to, just kind of for ease, I'm going to do that along the y-axis. Okay, it didn't show up that great on screen, but it's coming right to about right here. Okay. Then I'm going to take that out, and I'm going to look at z versus y. So I guess I'll do that. And so this is the partial derivative of z with respect to y, and really what I've done here is I'm looking at pretty much this. And if I wanted the actual value of the partial derivative at some particular point, say, I don't know, right here. Well, that's basically the slope of the line tangent. That would be right here. And so we say, when we say dz dy, we are, looking at a rate of change of z with respect to y, and we can kind of see it in this little zy trace. Okay? But we might be interested in what happens as we go, maybe not just towards y or just towards x, but maybe towards, like, I don't know, the northeast, right? We might be interested in how something changes as you head a direction that's not just one of the 4 cardinal directions, right? Or just north or east, right? There's going to be other directions we might want to head and find a rate of change on a particular surface. So that brings me to the definition of the directional derivative, which, you know, kind of the full definition is unwieldy, not good to work with. But then I will relate to you a theorem that will be really useful for you for computing directional derivatives, and then I will come back and prove that theorem later after I've given you the chain rule. So I'm going to actually just rotate a little bit so we've got a little more word to work with. All right. So we're going to call the directional derivative of f in the direction of a vector v, we're going to call it the derivative of f in the direction of v. And that's going to be equal to basically the limit of rise over run, limit of a difference quotient, limit as t goes towards 0 of f of x plus delta x, where delta x is moving in a particular direction. I'm realizing I'm kind of writing off the screen, so I'm going to kind of pause and readjust the position of the computer. And y plus delta y, where, you know, delta x and delta y are kind of heading in the direction that we're interested in, divided by minus f of x and y. It's like a net change in the function, kind of standardized by how far we moved in terms of t. And it's like, well, what does t even mean in this situation? So I'll draw you the picture. And then I'll write you, you know, something that makes a little more sense in terms of t. So suppose we've got a domain of a 2-variable function, okay? You think about the domain of a single variable function is going to be an interval on the real line. So the domain of a 2-variable function will be at least some region in a plane. So I'll just say, you know, suppose this is the domain of my function. And then I could, let's see, I could start at a point and I could get a vector from it. And what I need, basically what I need is I need for the length of this vector to be t. So I'm going to just say, you know, here, kind of the length of v is equal to t. Okay. Now, this is the direction that I'm interested in taking the derivative along. I'm interested in just bumping up the function a little bit, or bumping up x and y in that direction. So I want the value of t to go towards 0, right? And, you know, we make ourselves a little right triangle here and you know, call that an angle, at least with respect to something. And then this will be, this length here will be t cosine theta, and then this length here, this vertical length, will be t sine theta. So over here, what I'm really interested in is the limit as t goes to 0 of f of x plus t cosine theta and y plus t sine theta minus f of x and y, all divided by t, as t goes towards 0. So it's how much did f change when I just went a little bit in that direction. Okay. Right, and then I think at this point I don't really have much else to say besides to give you the theorem on how we're going to actually compute this thing. The directional derivative of a function f in the direction of v is given by the gradient of f dotted with the unit vector in the direction of v. So gradient f dotted with v divided by the length of v. Okay, And that's going to be how you will want to compute these things. So I'll work an example. I'm going to work off the same function over here. F of x and y is x squared sine of 2y. I will be interested in finding the directional derivative at the point where x is 1 and y is pi over 2 in the direction of vector 3, 4. So I'll write all that down. All right, so what I'm going to need two ingredients. I'm going to need the gradient vector at that particular point, and I'm going to need the unit vector in the direction of v. I think I'll do that first because it's going to be easy. Okay, if v is 3 and 4, the length of v is 3 squared plus 4 squared, which is going to be, or I guess the square root of that. It's the square root of 9 plus 16, it's the square root of 25, it's 5. So I've got length of v equaling 5, so the unit vector in the direction of v is going to be 3/5 and 4/5. Now over here I can use my formula for the gradient of f at any point x and y and get myself the gradient at the point where x is 1 and y is pi over 2. So gradient of f at 1 and pi over 2 is going to be, okay, well, let's see. 2 times 1 is 2. Times the sine of pi. The sine of pi is 0. Okay, so that's 0, and then 2x squared is going to be 2 times 1 times the cosine of pi is going to be 2 times negative 1 is negative 2. Yeah. Okay. And now what I'm going to do is I'm going to dot these things, which should be pretty easy, right? The directional derivative is going to be 0 times 3/5 plus negative 2 times 4/5. So, I have negative 8/5. Okay, and I think that's all I'm going to say about the directional derivative in this video. I'll let you go off and practice computing it. Actually, hold on, I've got one more thing to say about this. I'm claiming that the partial derivative of f with respect to x is no more than the directional derivative in the direction of, say, something on the x-axis. Okay. And I'll probably come back and show you that right where I'd drawn that picture. Okay. Same argument can be made for the partial derivative of f with respect to y, and I'm not going to make that here. So note that df dx is the same as the directional derivative of a function in the direction of I, like ijk 1, 0, 0, or 1, 0, whatever. Okay, and I can show you that because the unit vector in the direction of x is I. Okay, so equals gradient of f dotted with I, or dotted with 1, 0. Okay. But I know what the gradient of f is. I can also write that. That's fx and fy dotted with 1, 0, which is just going to be fx, which is the same thing as df dx. So that was the last thing I wanted to point out, was that you're kind of already familiar with two kinds of directional derivatives. That would be the directional derivative towards x and the directional derivative towards y. But that's all I got to say in this video.